20-3, this way. Orient yourselves this way. We're going to calculate the equivalent resistance for a mixed circuit now. That's all this is. So what we did in 20-2 with calculating REQ for series and REQ for parallel, we're going to do that for a circuit that's in both series and parallel now. Let's take a look and recall this information. This was from yesterday. We finished this yesterday in class. This last piece of info told us about the general rules for resistances. Now, these rules we're going to use for several different circuits that are connected in different ways. So we're going to see that if they're in parallel and series, what has to happen as a result. Okay, so let's take a look at an example of this to get started. So think about like in your house. This is, by the way, an old school microwave. That is a really old looking microwave, but it is. It's a picture in your text. Imagine a microwave, a blender, and a toaster, all on the same circuit. Okay, microwave, a blender, and a toaster. Now, what you'll notice here, if you follow the circuit, you leave the plug or the source of energy. Okay, leave the plug or the source of energy, go through the circuit breaker. The circuit breaker has very, very, very low resistance, almost negligible resistance, but this is what's able to sense if there's nothing to take on the energy from it. If there's nothing here, what will happen here is it'll feel a lot of current and it'll automatically flip open. Very low resistance means this would feel a ton of current if there was not some other element in the circuit. So if this felt a lot of current suddenly, it trips the breaker and your electricity goes out, but it doesn't start a fire. That's when you have to go back to the breaker and turn it back on, provided you didn't, surcharge something there. Yeah, that's fine. So what you're noticing here is that the microwave, the blender, and the toaster are all on the same outlet. And if one of your outlets goes out, like the top one, the bottom one does not go out also. Have you noticed that before? Have you ever tried to plug something in an outlet? It might not work, and you try the bottom outlet. Guys, focus up here. You try the bottom outlet instead of the top, or the top instead of the bottom outlet, and the other one will work. It's because the top and bottom outlet are parallel. So already, take a look here. What you'll notice is this. This branches off. The upper portion here comes from the microwave only. Look where I'm pointing, please. I'll zoom in. The upper portion comes from the microwave. The lower outlet is both of these two. So these bottom two are split on their own little parallel portion, and the microwave is on its own on the top. So when we look at the schematic, well, here's what you notice. Look, follow the flow. Exits, goes up, and it splits. Half of the flow goes to the microwave, or part of it, I shouldn't say half. Part of the flow goes to the microwave. The other part goes to the other outlet. But the other outlet is also split. Go back and take a look. Look at the bottom outlet. Isn't there a little three-prong splitter on the bottom? So you split it once, and then you split it again. So take a look at the diagram. The electrical circuit is split right here. A portion of it goes to the top outlet, which is only the microwave. The other portion goes to the bottom outlet, which is a combination of the blender and the toaster on the bottom outlet. So that then splits again. See the second split right here? So the first split is representing the fact that the outlet has a top and a bottom part of the outlet. The second split comes from the fact that the bottom outlet itself, which would normally, this would be the bottom outlet right here, the blender alone. But the blender is not the only thing on the bottom outlet. We use the little three-prong splitter, so the bottom outlet gets split further. So these two are both on the bottom outlet, coming from this portion of the circuit. This one is on the upper outlet, coming from that portion of the circuit. But then again, like I said, the bottom outlet then splits from here and here. Okay, the bottom outlet splits again into the blender and the toaster. So this is an example, okay, of a mixed circuit. We have a parallel within a parallel in this case. Let's look at examples that have parallel and series.
But in a situation where you only have two outlets, why would only one of them work there? Because if you only have two, but you're only using two objects, why would the top work and not a bottom?
They all work. Both the top and the bottom work.
No, I'm saying...
Watch, if the top if, for example, imagine the top outlet goes out,
Right.
okay? That cuts off this portion of the circuit. Well, the circuit still flows. Circuit still flows this whole way. Okay, it's still connected. So even if the top outlet went out, it doesn't matter. We just lose this branch right here. That's all we would lose. But the circuit would still be continuous.
Okay.
It would still flow. You see what I'm saying?
Yeah.
So if one of the outlets goes out, the other one still works with the diagram. All right. So the easiest way to do this, easiest way, is to look at the diagram and analyze it and say, is the circuit flowing from one resistor through that resistor right into another one? If it is, it's in series. So right away, the 3 and the 6 on the left are in series. Because follow the signal. Okay, we'll follow it out the left side. It flows here, hits one resistor, goes through, hits another resistor. There's been no branching off so far, so these are both in series. Up here, it branches off. Here's one branch, here's the other branch. So this branch is in parallel with this branch. Meanwhile, these two are in series in this little small portion right here. See how they're one after the other up top? So this is like a mini series circuit right here. I'll circle in blue. That's a little mini series circuit. This is in series right here. Then this whole thing with this is in parallel. Once we resolve this to be one resistor, we could then see that the entire thing is in series once we replace this with one resistor. Okay, so I'm going to erase all that and do it again. Let's go ahead. So let's start with the first one. The 3 and the 6 are in series. When resistors are in series, what do we do to come up with a replacement resistance? What's the rule in resistance in series? Go to your formula sheet or go to your notes from yesterday. Or the lab. Marco.
You do REQ.
Equals?
6 plus 3.
Good. Remember the rule for series is the sum rule. There's only 2 of these in series to start right here. So those really add up to give you? Good. Now, up here, these are also in series, right here. So I could replace the 6 and the 2 ohm resistor with a single resistor in that location. And since they're in series, what would that value be? What's 6 and 2? 8 up top. The bottom is not, yeah. Up top is 8. So, our new circuit. Go ahead and draw a new circuit, please. So what I'm going to do is this. I'm going to replace this with 9 ohms. That's the 6 and the 3 together. I got rid of the 3 ohm resistor here. And I replaced this with one resistor of 9 ohms. The other ones, this one is 4 ohms. It's the same. This one is 1 ohm. It's the same. This is still 9 volts. The top one up here should be 8 ohms. Because you're replacing the 6 and the 2 that are in series. So go ahead and write this down as step 1 on the side. On the side, write down the following. Resolve all resistors in series first. Resolve or combine, either word is the same. Resolve all resistors that are in series first. They're in series first. Now, what you'll notice is that the 9 ohm resistor, if this were one resistor, would be in series with it, with the other 1 ohm resistor. So if we can combine the 8 and the 4 and make one resistor out of that, we can make these 3 resistors in series. Now, the 8 and 4 though, what setup are they in? They're in parallel. You know that because there's a branch. When there's a branch going to more than one resistor, those resistors are in parallel. So how do I figure out what the equivalent resistance is in parallel? What's my law in parallel?
1 over Rs equals 1 over R1.
RP, yes. Okay, 1 over the resistance in parallel equals 1 over the first resistor plus 1 over the second resistor. This is why yesterday's lesson was so important for today's. It's the same thing we did yesterday with parallel. So the 8 and the 4 go in here and here. It doesn't matter which is which, makes no difference. So we get 1 over RP equals 1/8 plus 1/4 That happens to be 0.375, which is 3/8. It's an easy fraction, so if you want to do common denominator here, you can. This is 2/8 right here, plus 1/8 is 3/8. Okay, so you get 1 over RP equals 0.375, or 3/8. How do I get RP on my calculator? What was the way to do this? Yeah, good. So at this point, take 0.375 and hit x to the negative 1. The button below math on your calculator. It'll give you the reciprocal of this, and therefore giving you the reciprocal of this side. Okay, it's going to be 8/3 instead of 3/8, obviously. But what's 8/3 come out to be? 266? 266.
Yeah, 167.
Oh, you x to the negative.
Okay, that's really what you're doing physically. You could type in 1 over, but x to the negative 1 literally does 1 over for you. You should be familiar with that command on your calculator. Okay, we mentioned it yesterday, but I'm saying you should be familiar as in you should be ready to use it.
It's just negative 1, right?
Say again?
It's just the negative 1.
Yeah, it's the x to the negative 1 button on there. And x to the negative 1, any exponent to the negative 1 means 1 over the positive, right? You learn your rules of exponents. A negative exponent means make it 1 over the positive exponent. That's why it's x to the negative 1.
How many decimals would you usually want?
I would keep at least 2 for now because we're going to do more calculations though. So it turns out that the resistor at the top of the circuit could be simplified easily with a resistor of 2.67 ohms. So our circuit now looks like this. The 2 on the top here, one was 8 and one was 4, is now written as 2.67.
You're turning it into a series?
Exactly. So in the beginning, I looked and I saw that I had a 6 and a 3 in series here, and I made that 9. We had a 6 and a 2 up top, made that 8. Well, the 8 and 4 in parallel are really 2.67 on its own. Now these 3 are all in series, so what do you do to them? Just add all 3 up, and there's your equivalent resistance for the whole circuit. 9 and 1 is 10, so 12.67. Okay? So the whole idea behind this, simplify whatever's in series. Once you're done with that, simplify whatever's in parallel. Then you'll probably have more in series again after that. Okay, but start in series always. Start in series always. So what I want you to do, you have 2 minutes, not even 2 minutes. What I want you to do besides your homework, obviously, is practice the last example in the lab. But the homework for this section will give you more examples to practice with this also. Okay? This is one example. If you're really struggling, at least look at the other examples in the section in the textbook. Look in 20-3, or you could YouTube. If you YouTube simplifying series and parallel circuits, I guarantee you'll find examples of this. Okay? Make sense? Yes? Okay, tomorrow we're reviewing.
What about the 9 at the bottom?